Hello and welcome to Foucault's Pendulum for Advanced Experiments number 6. In today's video we'll be looking at what choice of bearing for our decoupling bearing. Now, in previous videos you would have noticed that we mentioned two types of bearings that I've been playing with: the needle point or the ball bearing point. Now in the needle point we have the advantage, we're guessing the advantage will be extremely small surface area. So our needle point, extremely small surface area. I'll just cut you to a slide there, you should see that. And our ball bearing will have the advantage of a ball bearing with a self-lubricating tube, oil-impregnated tube. So my gut feeling is, and I guess yours would be, that the ball bearing, although it has a larger surface area, it will be a better choice for the, as we just know from basic ball bearing technology. However, we're not sure of that. And it's almost impossible to measure that. As you notice that when I was trying different methods with the Pendulum pendulum, just that small piece of wire, which is 100 millimeters long, I could not detect any frictional change in either of these two bearings. It was just impossible to detect anything. We're talking about a very small, minute changes here, and compared to the surface, the rotation of the Earth and the measurements we're making, we're well into the noise of everything. So we've got to bring our system out of the noise as much as we can. And those other previous experiments, in number 5 in particular, we had the pendulum on motion, and we found that we had two critical points, A and B. We found in this zone here, between A and B, there was some sort of friction and coupling between the fixed pendulum and the Earth, which we clearly showed in experiment number 5. Now how that relates to the swinging pendulum is, in this green zone here, we are assuming, although we haven't proven 100%, that we're getting decoupling from the Earth. So the pendulum swinging in this area here is clearly decoupled, and we had no argument with it, but we have to check that. But as the pendulum begins to slow down, the friction of the decoupling bearing starts to take over and grabs the pendulum and starts spinning with the Earth. So it's no longer decoupled. Now, we're not sure, that might be insignificant. So again, we have to prove that. But the major issue will be is to make the choice of bearing as frictionless as possible. That will bring this red zone closer and closer to our stopping points. And the closer it is, the less significance it will have on the overall time and the swing. Because I can now safely say, from what I've been previously experimenting with, if the pendulum is experiencing any sort of friction, 25%, or a quarter of the way the swing, either end, you'll get, you may as well chuck this pendulum out. It's absolutely useless. It's a fake. Forget about it. Let's not move on, but my gut feeling, and from other experiments, that the pendulum works, and we can actually make it work by getting our friction very low, that we get decoupling from the Earth, and showing us a linear fixed frame of reference. Okay, now we'll just switch into our experiments now, and I'll just show you how my method is. I've found to pick the best bearing surface between these two, the point and the ball bearing point. So let's stay with that now and watch these experiments. Okay, just going over my setup. Basically I have a reduction geared DC motor driving a tooth belt and pulleys of different ratios. Now I can swap the large one to this one and back and forth to give me more diversity. I have my normal spline and my needle indicator showing the Earth going around, and my level indicators, which are very important to give me my levels either side. It's critical that that be levelled with a self-bullet level as well. I also have a variable power supply with a digital readout that gives me the voltage for turning the motor. Now I can vary the motor voltage with this trim pot here. So the concept will be, firstly before I show you the concept, I'll show you I haven't installed the oil impregnated point. This is the ball bearing point from a ball biro. So what I usually do is just a drop of oil into the reservoir, then place, this is a precision fit, mop up any oil. Now that will actually write an oil stream from that ball. So I'll just show you the concept without the clean pendulum. Motor goes around turning the indicator, which is the earth. I can vary the speed. Now what I will do is I'll put the clean pendulum on. And I'll accelerate the motor to a certain voltage, and then when the pendulum and the needle are in sync, I'll measure the voltage required to obtain synchronization, and that will give us a first indication of the bearing with friction. Obviously, if this was a frictionless bearing, no matter how fast this spline turned, this would just sit in the one spot. However, there is friction and there is coupling between the clean pendulum and the spline, even though it's very small with that ball bearing. And we're assuming this will be the better of the two bearing surfaces. But I'll now be able to get a voltage reading. So let's plug this in and get a voltage reading, and I'll give you a starting point. At the moment I'm going to 2 volts, and what I'll do is I'll just take it to 2.5 volts. Now watch this, this should become in sync at some time. As the bearing friction couples to the spline, you should start seeing the needle and the clean pendulum become in somewhat sync together. Now what we'll do with this one, we'll wait, although I'll put you through the whole sequence unfortunately, but fortunately a lot of people are requesting that I stop cutting out as much detail as possible. So I'll try and keep the videos, although they'll be longer, you'll see more evidence and more experimental evidence is what you'll be requiring to make your bearing. Just in the background there you might notice the clock is sitting at 6:14. I didn't realise what time we did start, but you can start seeing the pendulum and the needle getting closer and closer to synchronisation, which is extremely, to me, the first time I did this, I didn't expect it to go anywhere this fast. I would have thought coupling would have been at extremely small revolutions. That's why I had the gears the other way around, the large gear being driven off the spline, plus the 100 ratio gearbox in this thing. So when I first designed this, this, I was expecting extremely small rotational velocities. Now, this is quite shocking to see compared to what the Earth is going around at. We're still getting coupling at this extreme angular velocity. Now look at that compared to what our original clockwork motor driven experiment was. So now we're starting to see the needle and the pendulum starting to get closer and closer to synchronization. It's been about a minute running. The next video with the needle, I'll just quickly show you the specs straight away because you won't need to know the setup. And to me that's getting very close. There's a little bit of a lead on the needle. The needle is slightly leading the pendulum at this stage. In fact, it's actually gaining. What I'll do is I'll reduce the voltage now to 2 point. You can't see that's flickering. I'll reduce this to 2 volts. So we now got 2 volts driving our motor. And to save some time, I found 2 volts was the synchronization voltage. So drawing this out any longer, because I have been through this and know the results. So the next thing I will do, I will stop the motor and I will time the stoppage for the swing, the reversion, the swing time, I guess the revolution of the pendulum. Okay, look, there's very little difference between the pendulum and the needle at this stage at 2 volts, so what I'll do is I'll break using this timer, this stopwatch. I'll do the moment I stop it, I'll pull the okay, our timer's counting, and we'll just see how long it takes for the pendulum to stop. It's 13 seconds. (29, 30 seconds). (50 seconds). (1 minute). (1 minute 21). Now I have measured this before and it comes in almost consistent, which is a very good sign. So we now have 2 parameters to measure this friction with. Our voltage to decouple and our wind down spin time of 1 minute 21 seconds. Okay, I think that's enough for this, and we'll move on now to the needle point and we'll watch that experiment now. Alright, 6:55, and I've just gone through the process of changing over to the needle point bearing. Placing our pendulum on. As you can see, doing a static measurement, it's almost impossible to figure out the difference in friction. Alright, so just give you, while I'm just letting that settle down, just think about which you think will be the better of the two. The needle point with its very small surface area, or the ball bearing, using ball bearing technology and remembering that we're at a little bit of advantage compared to Foucault, who I don't think he used a ball bearing. He had some sort of system like this. Ball bearings weren't invented at the time he experimented, so here we go. I've set the voltage to start off at 2.5. Okay, bit of a surprise. At 2.5 I've already got synchronisation at this early stage too. So I didn't catch your time, but you may watch the time. I can go back over the video, but I forget what time I started, but we've already got synchronisation, so let's just go in jumps of half a volt. I'll take this to 3. Okay, we're at 3 volts. The needle and pendulum are still synchronised, so we haven't got decoupling at this stage. We'll go to 4. I'll go in. I know what's going to happen, so you're all surprised. So I'm going to jumps of 1 volt. Okay, we're at 4 volts. Slight breakaway during acceleration, but once the velocities becomes synchronised, we've got synchronisation still at 5 volts. So we're still coupled. The earth and the pendulum are still coupled. If you want to use the analysis, go to 6 volts. Volts. Alright, 0.5, that's where I found decoupling occurred. It happens predictably every time, which is a good sign, I guess. 6.5, you'll just start to see the needle advance ahead of the pendulum. It's very slow, but trust me, that's where it happens. Anyway, the comparison is so obvious now. It's the ball bearings is far much more better choice for our friction. Alright, I think I'll stop it now and we'll do a countdown, but we've got to remember this thing is travelling at probably 3 times the velocity that the ball bearing was set at. Okay, we're at 2 seconds. Twenty seconds. Fifty seconds. One minute. One minute 21, where the other one was. One minute 30. Okay, so the deceleration was massive compared to the ball bearing setup. We reached virtually took a minute 30 seconds to deaccelerate from that extremely high angular velocity. So without question the ball bearing is a better choice. We have now got a benchmark to start measuring other bearing surfaces and other experiments. I think the plane pendulum again is proving to be a successful analogue. Alright, I think there's enough information here to carry on to the next experiment, which will be hopefully giving you some more excitement. Probably maybe looking at the wire that holds the bulb and some data there. Okay, look, thanks for watching and we'll see you in number 7.